Hello everyone, welcome to MATLAB help session for homework 2. Today I will be solving this 4-bar linkage, and we'll be looking at the animation and the plot for the angular velocities for length 3 and 4 and xy component of the velocity for point P. So I started off by solving the 4-bar linkage like we did in class. So we have here the 4-bar linkage shown in this figure, and by defining all our variables, and then start solving by using the cosine rule to define the sides and angles. So we solve it for the angle AC by using this equation. So the first step that we're going to need to do is to define all the given variables. So in a new script, we'll start by clear all, close all, then we will start by L0, L1, L2 and L3. These were given in the homework. So we have L0 is equal to 7, L1 is equals to 3, L2 equals to 7.5, L3 is equals to 4.5, and we have the length of PA. PA, this side right here, is 4 centimeters, equals 4. And we have alpha, this angle right here is 35, so alpha is equals to 35, and we have theta 2 dot, the velocity of theta 2 is 5, so we can call that omega 2, W2 is equals to 5. And now we're going to start by implementing these equations to MATLAB. So as we can see that the question asks for the range of the input angle should be at least 360. So this is the input angle, theta 2, the angular velocity of the input, link 2 right here. So this theta 2 goes from 0 to 360. At least this is what we are going to start with. So we have theta 2 is equals to, goes from 0 to 360 with a step of, you can vary the step as you need, it just goes 2 now. And now we are going to implement these equations. So we'll have 4I equals to, starts from 1 and goes up to the length of theta 2, and what's that doing is that we want this loop to keep running these equation as long as I starts from angle 1 and goes up to 360, which is theta 2 right here. So we'll start off by adding the equations AC. So we have AC of I will be equals to the square root of L0 all squared plus L1 all squared minus 2 times L0 times L1 times cosine in degrees, which is cos d theta 2 of I. So that will take care of the first equation here. And then the second equation, beta, so beta of I equals to the inverse cosine is called as A cos D of L0 all squared plus AC of I all squared minus L1 all squared, and all of that is divided by 2 times L2 times AC. And then we have psi of I will be equals to A cosine degrees times L2 all squared plus AC of I all squared minus L3 all squared, and all of that is divided by 2 times L2 times AC. Okay, and then we have lambda so we have lambda of I will be equals to A cosine D of L3 all squared plus AC of I all squared minus L2 squared divided by 2 times L3 times AC. Okay, so now we have these first 4 equations. We're going to define theta 3 and theta 4. So theta 3 will be psi minus beta. I tried to explain it here because theta 3 is this little angle right here between the x-axis and the linkage AB, and this whole area angle is called psi. So if you subtract psi, because psi subtracted by beta, since beta will be equal to this angle, will give you theta 3. So we'll have here theta 3 of I will be equals to psi of I minus beta of I, and theta 4 of I will be equals to 180 minus lambda I minus beta. Okay, so this essentially will take care of all these 6 equations. And now we need to define the thetas, theta 3 and theta 4, when theta 2 exceeds the 180. So when it's going in the other direction below the x-axis. So that will be if theta 2 of I is larger than 180, that means that theta 3 of I would be equals to psi of I plus beta, and theta 4 phi will be equals to 180 minus lambda of I plus beta of I. Alright, we just flip the signs here. And we're going to end this if loop. Now our next step to do is to define the joint positions. So now we need to define joint position. So we can define the joint position just like we define any regular vector and then x y coordinates. So we have joint O is the position of joint O on the x-axis is 0. Same thing goes for O y, and then joint A and the x-axis will be the position of this joint plus L1 cosine theta 2, and same thing for AY will be the position of that joint in the y-axis plus L1 sine theta 2. So we'll do that here. Okay, so we have OX of I is equals to 0 and OY of I is equals to also 0, and we have AX of I is equals to OX of I plus L1 multiplied by cosine in degrees of theta 2 of I, theta 2. Okay, and same thing goes for AY. I'm just going to copy that and paste it. So AY will be equals to OY L1 sine, this would be sine theta 2. Okay, and now we need to define bx and by. So we're going to have bx of I is equals to O of x of I plus AX of I plus L2 cosine of theta 3 of I. Okay, I'm just gonna copy that. Paste it here, and then we're going to change the variable to be by and oy, ay, and this will be sine, right, for these two equations. And now we're going to put cx and cy, so we have cx is equals to L0, right, because this is the position of joint C on the x-axis. It's far away from the origin by L0, and then cy will be equals to 0. Now we have to define the joint px and py, point P in the x and y direction. So we have px of I will be equals to ax of I plus LAP that we defined earlier, this linkage right here, LAP, times cosine of alpha plus theta 3. Right, this linkage is far away from the x-axis by alpha and theta 3, so that's why we add them together. and then py of I will be the same thing. So I'm going to copy and paste it and just change the variable. Paste it. So this will be ay lap sine p. Okay. So now now that we have defined the linkage position and the joint positions, we can go ahead and plot that one to meet the deliverables of question number 1. So we are going to plot. Okay, so we're going to plot the first joint, which is OX, Y, and AX, Y. And the second joint, the same joint but in the Y direction, Y, X, Y, I. And then we're gonna move to this linkage right here. So we have AX. Actually, I'm just gonna copy these two, paste it. Okay. So we have here, we're gonna change this to AX and BX, and then AY and BY. And now I'll paste it again. Now we'll change that to BX and CX and CX, and then BY and CY. I'm going to define the line width. Line width, make sure to type it like that. Be thickness of 3. I'm going to close the parentheses. I'm just going to define the plot diameter. So we want the grid to be on, and the axis to be equal, and we want the our axis when they are plotted to be in this range. It will be -5, 15 on the x-axis, and -5 and 10 on the y-axis. And drone out and hold off. Alright, let's see if it's gonna run. Okay. Yep. Okay, so now that we animated the 4-bar linkage for the first one, now we're gonna animate the upper part. So we are going to print that part. So we're gonna plot the point P. So we say, okay, so we say plot AX, of I and px of I and ay of I and py of I and oops, we got a bracket here. Okay. And we're also going to put bx. Just going to copy that and paste it. So I'm going to change that one to bx, and this one to leave it as px. This one will be by. This one will be py, and change the line width. Copy, paste that here. Okay, let's do it. 2, 3. Okay, now we're gonna see if that one will run. Okay, now we got it. We got the point P. So AX and PX, it's for that linkage right here. So defining point AX here and PX here, and then AY and PY is the same joint but in the Y direction, and then BX and PX, it's that joint right here. Here's P and here's B. So same thing for X and Y direction. So now we have finished part 1. We're gonna do this one last, and here's for part 3. Plot the angular velocity of link 3 and 4 versus the input crank angle. So we know that the angular velocity omega is equals to v over r, and what we need to do is to define r in terms of the linkage 2 and 3. So this is the position of linkage 2, which is L2 cosine theta 3 and L2 sine theta 3 in the x and y direction, and this is the position of L3, negative L3 cosine theta 4 and negative L3 sine theta 4. There's if you can look at it here, for linkage 2 and linkage 3, these are the given position, and for the velocity it will be negative L1 alpha cosine theta 2. This is the velocity in the x direction, and this is the velocity in the y direction of the input crank right here, theta 2. Okay. Sine of theta 4. Alright, so now what we need to do is implement the velocity equation. So we have v will be equals to negative L1, let's put a bracket here, so it will be negative L1 multiplied by omega 2, which already defined it before, which is 5, it was given, 5 radians per second, times cosine d of theta 2, 2 of I, and negative L1 times 5 times sine d of theta 2 of I, first bracket. Okay, and now we are going to type this equation, which is omega equals to the inverse of r times the velocity. It's the same equation, this one, but we just raised the r into the numerator. So we have omega I of all the columns will be equals to the inverse of r multiplied by the velocity. So now we need Let's see if it's running. Okay, it's running, no problem. Now Omega has the solution for omega 2 and omega 4 that we solved it from here. So we want to call omega 2. So omega 2, we want to store this value right here. So omega 2 of I will be equals to W, which is omega I, the first column, and then omega 4, which we just solved for, will be equals to omega I, the second column. Now we can run it. Okay, it's running, there's no problem. You can see that omega has two values, omega 2 has one value, omega 4 has also one value. So we can plot these values. So I'm going to go outside that loop. So we're going to say figure 2, plot theta 2 on the x-axis and omega 2 on the y-axis. And we're going to have that line width 3. You can get creative here with any way that you want to plot it. And we're going to add a label. I'm going to add a label. For x will be theta 2. And for y, we're gonna add joint AB coordinate. Alright, let's run it, see if it will plot it. Okay, now we have the same thing for omega 4. So now we're going to plot omega 4 and we're going to add a title. Angular velocity for linkage 2. Same thing here. This will be linkage. Actually, this is, yeah, 4, linkage 4. Oh, it's figure 3. All right, it looks good. So now we need to plot, we need to find the velocity of point P in the x direction and the y direction. And for that one, what we need to do is, alright, so now what we need to do is to find the velocity of point P in the x, y direction. And for that, we will solve for the position of px and py, and then take the derivative to find the velocity. And here I defined a new variable, theta 5, to be equals to alpha plus theta 3. So we'll go ahead and code these two lines here. So we first we're going to start off by defining theta 5. So we have theta 5 of I will be equals to alpha plus theta 3 of I. And then we're going to start by writing p dot x, so the velocity of point P in the x direction. So we'll say v p in the x direction of I will be equals to negative L1 times sine degrees of theta 2 of I multiplied by theta 2 dot, which is omega, which was given in the problem. We defined it in this code as W2, minus LAP, in our code it's LPA, times sine of theta 5 of I times theta 3 dot, which is in our code omega 2 of I. And I'll go ahead and copy that and paste it right underneath, and that will be VPY we'll change that to cosine. This one will be positive, and this one will be cosine. Oops, again. Okay, so now we need to print those to plot them. So we are going to copy figure 3, paste it, that will be figure 4, and we'll change that variable to be VPX, and that will be the x component of velocity of point P, so it'll be the x component. X component of velocity P and we'll do another one for VPY, figure 5, VPY, that would be Y. Let's run it. Okay, I'm missing a parenthesis here. Let's run it. Okay, that looks good. These are the two new plots. Now if you want to run theta more than 360 degrees, you will need to add another loop here. If theta 2 of I is larger than 360, so theta 2 of I will be equals to theta 2 of I minus 360. And that that ensures that theta 2 will always be in the 360 range. So let's do another run. good. I hope that was helpful for you guys. Feel free to play with the code, do anything you would like.